Hello again. So, you guys seem to be pretty confused with kinematic equations. So, I'm going to make a video showing you guys, the different kinematic equations, where they come from, how they function. So, first kinematic equation, actually, better idea. Explain where they come from first. So, our kinematic equations are equations we can use when we have constant acceleration. Now, so I'll put right here, need constant A, meaning I need constant acceleration. Now, we have these four equations that we can use in pretty much any situation with constant acceleration. Now, most often this is referring to gravity. Most of the time when we're using a kinematic, a common example would be with gravity. Now, this would be a pretty common example, but another example would be like, say, a car starts from rest and accelerates at a rate of 3 meters per second squared for a time of 4 seconds. What's the final velocity at the end of that? That would be a common question for a kinematic equation. It's equally valid because it says that there's a constant acceleration through the entire time. Now, these kinematic equations were created using the base blocks we learned earlier, using delta x, which is displacement, delta v, which is velocity, or I should just put put velocity. The reason I removed the delta there is because that really represents the change in velocity, and we're going to be seeing velocity more as a final and initial value when the acceleration is constant. Then we have A, which is our acceleration. We have T, which is our time. And those are pretty much the main variables that we're going to be working with here. Now, just so you guys are caught up to speed, and just in case some of you probably right now are like, Mr. Manti, I still don't even know what on earth you're talking about. So, displacement is, again, how far an object is on a straight line displacement from its original position. And this would be in meters. More specifically, it's a length. Sometimes I'll put it in miles, sometimes I'll put it in kilometers. I could even get real weird and put it in like fathoms, I think. Actually, no, I think fathoms is a unit of depth. Anyway, you can express it as a unit of length. Then we have velocity, which is meters per second, or more specifically, a unit of length divided by a unit of time. When we look at velocity, we're expressing our displacement divided by our time. How far you are displaced from your original position, or how far an object is displaced from its original position, divided by its time. Acceleration, meters per second squared. Or another way that I like to see it, meters per second per second. And this is a change in the rate of the velocity. It means the velocity is changing relative to time. And that makes sense because we're looking at acceleration. Acceleration is a change in velocity. It would make sense that, velocity changes. Another way of writing this is length divided by time squared. And last we have time. Time is just a unit of existence, and we measure it in seconds, and it's an independent variable. It's happening no matter what. And some people might even argue that it's an artificial construct of man, but realistically we had to find a way to quantify existence, so we use time. We base that on the solar day, but more specifically, as of recent existence, we have been able to really measure it relative to the speed of light. Pretty cool stuff considering light is the fastest thing in the universe. Okay, so I'm going to leave you guys here for right now. I'm going to make another video going more into the equations.